Okay, so the first thing I want to talk about is enumerations. And I don't think I've covered this so far. Hopefully it wasn't in any other videos. Does anybody remember me covering enumerations? Okay, I'll take that as a no. So many languages provide a way to have a fixed set of values as enumeration values. Uh, Java extended that a little bit more than some languages, and Kotlin does very similar. But let's take a look at a really simple definition here. Let's say that I was defining a card game. I could start off with something called an enum class, suit, which is a little bit different than what you might say in Java. In Java, you just say enum, but in Kotlin, you say enum class. And then I could say spades, hearts, diamonds, and clubs, kind of like that. And poof, now I have a set of values that I can work with. So if I define my little main function here, inside here I could say val suit equals suit dot spades, just like that. And there's a few things that I can do with this. If I say println suit, let's take a look at what that looks like. Spades. Now if I also say suit.name, let's see what it says. Notice it's exactly the same. Every one of these enumeration values has a name associated with it. We can also get all of the values. Whoops, wait a second. Oh, let's actually do it that way. And what is he not happy about? Oh, entries. Wow. Oh, that's new. I learned something today. That's always useful. This is going to be an array of all the values. So if I take a look at it, we'll see that array printed out as spades, hearts, diamonds, clubs. And each one of those, you could grab individual items from there. Well, let's grab that one, which should be diamonds. We'll see that print out. And you can also figure out which position these things come in. 0, 1, 2, and 3. So if I come in here and say suit.ordinal, and what is he saying is now? Suit.ordinal is, oh, well, because this is a val. But suit.ordinal is the one that'll get you that value. It should return a 0. And there we go. So this is super, super basic enumeration values, and it really just gives you a finite set of values that you can reference by name and not have to worry about the value number on them or anything like that. So any questions so far? Now in both Java and Kotlin, it can get much more interesting. You can actually define properties on a suit or on a enumeration, and you can define functions on it. Now this is one of the very few places in Kotlin where you absolutely have to use a semicolon. Semicolons are usually optional. You can use them in similar positions you would in Java, but they're frowned upon in general. Here you have to use it as a separator between the values and then anything you're defining as far as properties or functions. But typically with properties, what you'll do is define them in a primary constructor, very similar to the way that you would for a class. So I could say val fancy name is a string, kind of like that, and poof, I now have a property. But notice how all those values have gone red. Let me actually, before I do this, I'm just going to make a copy of that. I'll call it suit1. And so now suit here, I'm going to say val fancy name is going to be string. And now each one of these values is invalid because I haven't specified that required property name. So for each one of these, I'm just going to separate them onto different lines now. Let me get rid of that semicolon that's not needed up there. And here I don't need a semicolon yet. So we'll say here it's going to be spades or yeah, something like that. And then we'll say hearts and then diamonds. Oh, come on. And clubs. And I could even get, you know, a little fancier and put the emojis in there. Like, let's say that I did something like that. And These are not allowing me to copy them as easily as I thought they would. And then we could do that. Whoops. And then we can do clubs. So maybe that's the fancy name there. And so now if I run this, that's the basic name, but I can also print the fancy name because now it's a property. And we see spades with that nice little emoji on there. Yes, Luis. Well, what enumeration is useful for is just if you want to have a fixed set of values, especially if you want to use them in like a when. So down here, if I came and had a when expression, then what I can do is add all the remaining branches and have an exhaustive list of possibilities. If you're using values in a set or a map or something like that, you're going to have an else because you're not going to have an exhaustive set of values. So that's one reason you might want to use these. I'm going to show you a little bit later. I prefer to actually use sealed interfaces or sealed classes now, mainly because you're not required to have this qualification on things. You just have top level objects. But this will end up giving you mainly the big advantage here is you have an exhaustive set of possibilities, so the compiler can actually help you out, help you choose things. Before enumerations, you'd quite often see people define constants. So you might have like const val, which, this didn't happen in Kotlin because we've had enumeration since the beginning, at least as far as I know, as far as I remember. But, you could say something like this, and then hearts, diamonds, clubs. And this was pretty common for people to define, it could be integer values, could be string values. And the problem with this is that these cannot be resolved as exhaustive because they're just treated as ints. And so you'd have to have an else clause inside your where. That's one of the big reasons for it. It's really, it also ties things together that you only can have these values when you're talking about suits. Somebody could say val suit equals 42 using a case like this, and that's perfectly valid code, but you're not restricting it to a set of values that you want to be able to use. Did that help? No problem at all. Yeah. Now, one of the disadvantages of an enumeration is that it can cause some really nasty problems if you end up adding things to it later on. So if you look at that when clause, for example, here, if I compiled a application or a library, let's say a library. Let's say I compiled a library that's using somebody else's enumeration from a different library. And so when I create my library, I have this when clause set up and everything's cool. But let's say later on, the library I'm depending on adds something new to that enumeration. Now I'm not handling it. And unless I recompile, I won't be handling that case. And that can come up with an error depending on a runtime error, depending on how you're using the when, where it would have an unhandled condition. If you had an else in there, typically one of the things that is still a good idea if you're using enumeration here to protect is to have an else that throws unknown thing exception. You create an exception to say, I'm going to throw this. Let's say throw, there we go. You'll create a brand new exception to handle that and have that as a catch-all. Whatever you do, don't do something like have the last value be the else, because then if a new value is added, it gets treated as that last value. If you're defining a enumeration in here, a good practice would be to put an else there anyway, even though it's not needed, just to catch problems if somebody actually changed that enum. Hopefully that helps a little bit. Okay, so we've added in the fancy name. We printed out the fancy name. We can have functions in here as well. Now, if you're having internal properties, I should actually note really quickly here, don't put a var on there. You actually can. So if I said suit.fancy name equals something, you can actually do that. And that's generally a really, really bad idea because each of these values is a singleton. It's something that should be, you have focused access to it. Everybody can get to it. But you really should treat it as immutable. Otherwise, it doesn't quite feel proper from an enumeration because you're kind of tweaking something that should have been a fixed value. So don't do that. Always use vals. Now, as I was saying, if you wanted to, let's go ahead and call that suit2. If I wanted to add in any type of functions, I have to have a semicolon there to separate the values from the function definitions. So in there, I could actually define a function, let's call it trumps. And this one would be choosing, does a given value trump another value in a card game? Now, typically spades is stronger than hearts, hearts is stronger than diamonds, diamonds is stronger than clubs, that type of thing. So I'm going to say other suit. And inside here, I can return a Boolean. I could say return ordinal is less than other dot ordinal. And so it's just going to tell me which one is worth more in the card game that you're dealing with. Now, of course, we could also reduce that to a slightly simpler single expression format for the function. So in this case, I could do things like, let's say suit and suit2, and suit2 will be clubs. And then I could say println suit.trumps suit2. And we should see that say true. There we go. Oh, there's the exception. Operation is not implemented. Where is that coming from? Oh, because I'm calling the to-do, duh. That's what the to-do is supposed to do. Okay, there we go. Let's run that again. And we'll see that trumps is actually true. So this is actually very useful, and you can do it in Java as well as in Kotlin. Very, very similar type thing. And every instance of this suit has the same functions, the same properties available to it. Now, if we compare that to when we're using a sealed interface or a sealed class, there's some pretty big differences what happens with this. So if I, let's actually go ahead and copy that. Oh, I made that in week 10. Shoot. Had the wrong file open. Let's do it in week 1. And I'm going to copy it to week 2. But let's change this over to using a sealed class or a sealed interface. And the difference between a sealed class and sealed interface is, do you want common data that you've actually defined? Or do you want to just define the traits of the objects that you're defining? If you define the traits, then every single instance, every single class you define that extends that interface has to actually implement it. I'm going to start with a sealed class here because I want to keep this fancy name type thing. So I'm going to say sealed class, suit, and we're going to have val fancy name, just like we did before. And can I do the abstract? I can't remember. Let's see, does he like that or not? Oh, sealed is abstract already. Oh, interesting. I didn't realize that. I'm learning a lot tonight. This is really cool. So let's put that trumps function in there. Well, actually, we don't need to have that be abstract for this. What is he complaining about suit? Oh, he's redefined, right? Yeah, okay. So one of the things you'll notice here is we no longer have that ordinal. Each one of the values is going to be separate, so we're going to have to define some way of determining which ones have higher values than the others. So in here, what we might want to do is say private val, let's call it rank, for which one's going to be higher than other ones. And then in here, I could say rank is less than other.rank. Okay, we don't need this guy. We don't need that. We don't need this one down here. Well, I can define I'm going to keep that for my fancy names for the moment, just so I can define those guys. And let's get rid of him and him. So now we're going to define the actual subtypes of this. Each of these, I could define them as a class or I could define them as an object. If I define them as a class, that means I could have multiple instances of it, which really isn't what I'm going for here. I want to have single objects, singletons, that we can actually talk to and say spades, hearts, diamonds, and clubs. So I'm going to define those as objects. So I'm going to say object spade is going to be a suit. And we'll notice the little error it's coming here because I'm not passing in a value to the constructor. So I'm going to hit my Alt Enter and say, oh, he doesn't give it to me, does he? Oh yeah, constructor invocation. That's right there. And let's, let's do this. This might be a little simpler. Spades, hearts, diamonds. And convention-wise, typically with enumeration values, you have them all uppercase. In a lot of times, I tend to make the enumeration values be mixed case anyway. But when you're doing objects, the convention is an uppercase letter, lowercase letters afterwards. So these are all going to be :suit, just so I don't have to copy all those emojis anymore. And I need a ranking on these. So let's say 1, 2, 3, 4, something kind of like that. And what is he kind of, he wants data object in front of that. So we'll do this. That just gives me things like the equals hash code and the print. And let's get rid of our commas. And then everybody should be happy. There we go. So this is how we might define the same kind of thing using sealed classes or sealed interfaces. So down in here, instead of this, I would say spades clubs. And notice I don't need a qualifier on these. Now, I don't have name and ordinal or entries. I could, if I wanted to, expose the rank. Might be fine. Can get rid of that. Or we could keep it just private, either way. So now instead of ordinal, I'll say rank. I don't have any base name anymore because the name is actually the type up here. So I could either define another property if I wanted to have that base name, or just go ahead and use the fancy name that's passed in. I'm going to go ahead and get rid of that. Now I also don't have any type of list that I can use of these. There's a fixed set of values because with a sealed class, you can only have subtypes defined inside the same module. But that's actually one of the bigger advantages of a sealed class. I don't have to define these all in the same file. I just have to define them all inside the same compilation unit, which is going to be the module. So it could be any of these files could define these guys, but some other library couldn't define new values. So that might be useful if you wanted to spread out where these definitions appear as opposed to with enumeration. They all have to be defined inside those curly braces. If you did want some kind of a list of these guys, you'd have to provide it yourself. So you could have something like a val suits equals list of, or array of if you prefer, spades, hearts, diamonds, clubs. And then in this case, I could say print out suits or suits sub 2, something like that. And let's just run this just to see that everything looks okay. So we see spades, hearts, diamonds, clubs being printed out. And, oh, well, yeah, of course. When the toString on this is just going to be the name of the object with the data object. So you wouldn't have the dot name. You could just actually print the value itself. And that prints out that. And then here's our fancy name. Here's our rank. Here's our list of guys. The suit sub 2, and if it trumps or not. So we're having very similar functionality. Also, when we use the when, we have an exhaustive list again. So what is he complaining about there? Why is he not giving me? Huh. This feels like an Android Studio bug or an IntelliJ bug, because I should have an option to include the specific value. So I could say spades. Let's see if he's now going to allow me to add others. Huh. That's very odd. Maybe if I said val x equals. So he's letting me do the else branch, but he's not giving me the exhaustive. That's really interesting, because I'm pretty sure that this used to work. Oh, actually, what the problem is here is suit is of type spades because of the way this is defined here. I have to actually define this as :suit. And now I believe this will let me do what I want to do. Add remaining branches. There we go. Now it's exhaustive. So that's what I needed to do there was, because of the type inference, spades is an object, which is a subtype of suit. So I actually had to explicitly give a type on suit in order to be able to use that exhaustively there. So very similar types of things, but then you get into the big advantage of something like a sealed class or sealed interface. Each of these subtypes can define their own properties and their own functions. So you can do different things with each one. Now for the suits here, it doesn't make any sense, but as we saw when we were defining mammals and cats and dogs, we could have them do different things. And that's huge, because then in here, when we get to these actions that you can perform based on the types, it does a smart cast, and you can directly use suit dot whatever the functions are inside of these subtypes. So just to kind of show that real quick, if I came in here and said fun a, and maybe said println a, and println, yeah, a, and then let's do the same kind of thing for diamonds. Note that I'm not doing it anywhere else. I don't have to have the same functions in all these types. I can now come down here, and if I'm clubs, I could say suit dot, oh, clubs didn't define it, did he? It was spades. I could say suit dot a. And that is a good question why that is not working. Spades defined a. Suit is of type suit. Why did it not smart cast? I am confused as to why that did not smart cast. I'm just going to explicitly, for the moment, put this in. I shouldn't have to. It should be smart casting. Maybe it's getting confused by the to-dos, but let's just see here. Suit dot. Huh. I'm going to have to try to figure out why that's not smart casting, because that should. Because if the suit is explicitly diamonds, I should be able to have the function on there. What if I did an is? Oh, interesting. So apparently, when it's doing the value comparison for these objects, it's not treating it as a type. Huh. I'm going to have to talk to the Kotlin folks and see if that is intended behavior. Because if I explicitly say is diamonds, I'm doing a type check. And so now you can see it's smart casting with a little green there. But if I compare against the value itself, it's not. That seems like that should, and I thought it used to when I've tried this in the past. But, worst case, you can always explicitly cast it. If you want to use the smart cast, it looks like you're going to have to do the type check like that instead of the explicit value check. That is very interesting. I'm going to send myself an email here real quick so I remember to look at this. Kotlin bug, question mark. Okay. Yeah, I wonder if there's a reason for that. Okay, well, I will try to figure out what the deal is there. But this is one of the advantages you can have with the sealed class or sealed interface. You can have different functionality based on it. And as you cast those values, you can use the different functionality as opposed to an enumeration where all the values have the same functionality. Okay, any questions in that? Okay, so that is all I wanted to talk about with enumerations. We're going to use them in a little bit here. But what we're going to look at now is something called builders in Kotlin. And before I talk about that, I want to talk a little bit about domain-specific languages. And this is something I like to bring up as often as possible because it's something that not everybody realizes exists. And the whole idea with a domain-specific language is to have a way for somebody to specify something in a more natural format. And the somebody could be a programmer, or it could be a subject matter expert. If you think about math, the way you write math, that's a domain-specific language. Mathematicians and then people who are doing math use certain notations to write things so it's clear to each other exactly what they're talking about. We can do this in programming as well. We can think of kind of, each different programming language as a general language that people use. It's not tied to any specific domain or specific subject that we want to talk about. For doing a domain-specific language, we can make these either internal or external. And internal ones are defined inside a programming language itself. And this, Kotlin supports this. That's actually pretty useful. Now, if we take a look at our build.gradle.kts over here, this is a domain-specific language. We've defined a language inside Kotlin that helps us configure the build. You'll see things like this where it says dependencies, curly, test implementation, blah, blah, blah. This is a way of specifying a build inside of a programming language because this is actually Kotlin code here. This one's not particularly interesting. How do you think that this is defined? What might be the definition of dependencies? Any ideas? So dependencies is a function that takes a single argument that's a lambda. The lambda has a receiver of dependency handler scope and no arguments coming into it. And then that dependency handler scope has a test implementation function defined inside of it. So that's just a function. And the thing that's nice about it is using this external curly brace syntax like this, it makes it look more like you're defining a scope on something. And you actually are, because this lambda is only being run inside this dependencies. The stuff that you define inside the lambda isn't visible outside of that lambda. So this is a very simple DSL. This would be an internal DSL because we've defined it in terms of Kotlin language constructs. We're going to be defining something that's a little bit more interesting than that. It will be, where is the one that I wanted to? Here we go. Let me go ahead and bring this guy down. So this is going to be something that we're going to define, and this is a little language to define a state machine. And that is being defined inside of here. And so if you take a look at this code, it's actually pretty interesting the way it's defined here. So we're defining state machine, and that of course is going to look like a function defined there, right? Actually, he goes down to there. So state machine is going to be some kind of function that takes a lambda. But then we start looking at all this stuff inside here. Some of this almost doesn't look like a programming language. You know, electric off goes to not powered. Things like that don't look like what you'd normally see in a programming language. In this particular case, goes to is called an infix function that we're using there. But there's a lot of other things we can do here to try to scope things. Transitions here is a function as well. So we're going to see how we're going to get to this. We're going to kind of build our way toward that. Let me get him out of the way. Put him up there. So I have something I can work with. There we are. So what we're going to do is we're going to start, for talking about a state machine, we're going to use our enumerations that we just talked about to define different states and different events for translating between them. The thing that we're going to be modeling right now is going to be a clapper, which is a little thing that you put inside an outlet. And when you clap once, it turns it on. You clap twice, it turns off, something kind of like that. So this is something that, depending on if you're clapping or not, it can toggle the lights on, or maybe it doesn't have any power coming into it. So we're going to have different states that we have to associate with this. So let's take a look here. Get rid of him. An external DSL is defined outside the programming language. As a brand new language. And let's take a look at a little example of that. I think that's what I wanted. This is a little language called Antler. And Antler, it stands for another tool for language recognition. It's generally used to define a parser to pull in information for a language. So we'll see that we have all sorts of very strange looking syntax here. This is syntax for the Antler language itself. And in that Antler language, I'm actually defining a brand new language. It's a very, very simple language where for a text adventure game here, where you can say get something, examine something, drop something, go somewhere, get something from something is an option here. And if you looked at the phrases that I'm defining here, that's a brand new language. That's a domain-specific language for how to interact with this little adventure game that I was defining. So this might be, you know, we now have kind of like languages within languages. We have the language of Antler defining the language of our adventure game. And this gives us a way to very naturally interact with the game. You know, someone can type it, you know, get letter. Someone can type examine room. You know, there's different words they can do, or different phrases they can type in because I've defined this nice little language. So this would be an external language. We're not going to deal with that anymore here. I just wanted to mention that that's an alternative. In Kotlin, we're going to be defining an internal language, and we're going to use it for a specific task. We're going to use it to build something, and we're going to use it to build a very specific something. So to start with, let's define an enum class, events, and he is going to have electric on, electric off, and clap. Those are the events that we can have. And then we'll have an enum class, states, not powered, powered, and whoops, lights on, something like that. So it's the three states that we can go through for these things. And let's define our state machine here. So we're going to need to have some data somewhere to keep track of our state machine. So for right now, I'm just going to use some global variables. So I'm going to say var machine is going to be a state machine. And he starts off at null. And we'll just define a class state machine up here for the moment. We'll fill in some details later. And then we can say var current state is going to be a state is null. And let's see, was that what I wanted to do? Where was state defined? So let's define a class state up here. There we go. And let's add in a var current. Well, we'll keep that for the moment. Let's define a set of functions that are going to help us build up this state machine. So I'm going to define a fun state machine equal, and inside of here, we'll say machine equals state machine. So we're just having a little helper function here. This is a function that builds a state machine for us. Kind of simple, kind of brain dead for right now. And let's put that in a main. So we're going to start off in here by saying state machine. Yay. So that should initialize this state machine variable for us. Now that's not doing anything at all right now, but we're going to build up things here. So the next thing we want to do is be able to add states to that state machine. So I'm going to add in a fun state class, and inside here, I'm going to give it an ID, which is just going to be a states guy. And let's say inside here, current state equals state passing in the ID. Now that means we need to improve our state class here to have that state ID, which is represented by that enumeration. And current state needs to be a var. There we go. So now what we can do is when we're defining this state machine inside of our main down here, we can now add in some states. So I can say state lights on, lights off, or powered, and not powered. So boom, I've defined those states. Now, what I want to do to start with here, just to try to make this look a little bit more contextual, is maybe just indent these guys. Now, of course, if I reformat my file, it's not going to work. But just for now, just for looks, let's put that there so it looks kind of like we're trying to say these are states in the state machine. And what I also need to do is have some way to associate these states with the state machine itself. So my state machine class needs to have some data inside of it. And so this class is going to have a set of states. Let's say val states equals mutable map of state to state. So this is going to be mapping based on the enumeration value to a specific state object that wraps it. And let's have a current state in there. I actually had the current state up there. Why did I do it up there? Let's put them inside there. So we have our current state defined there. And we'll put some data in here for handling it and actually running the state machine a little later. So of course that makes this not work. So I'm gonna have to say machine.currentState. Uh-oh, machine's nullable. So machine question mark dot current state. So if I have a machine, I can set his current state. Isn't that fun? Now, of course, what this means is if I run these functions in the wrong order, I'm kind of hosed. So I could do something in here like require not null machine and have a little thing here saying you must define the state machine before defining states. Or let's say must initialize. So kind of gross, but that should work. Now, little question on this. If we look at require not null, he has this contract that says if I return successfully, that means that the value coming in is not null, which should allow for smart casting, which is kind of cool when that happens. But if I go ahead and remove that, it's now telling me, nope, it can't smart cast because machine is mutable. And something else could have changed it at the same time that this function was running. Now, if machine weren't mutable, we'd be able to actually use the smart cast there. But because we can't use the smart cast, we have to explicitly use that null safety reference. Okay, so that's our state getting defined there. So far we have something looking like this. Now let's try to define it so we can actually say when a certain event happens, I want to go to a different state. So what I'd like to make this look like is something like on events dot, let's see what this is, lights on, let's say electric off, go to states dot not powered. So I'd like to have something kind of like that so that when I'm in a given state, if an event happens, I go to a different state. And you'll notice this is starting to look a little bit more Englishy. We're not near our end state at all, but it's approaching something that's more readable. Now, of course, if I reformat this, everything's in the same column, all bets are off, but we're going to fix that later on. So let's take a look at these different functions we're going to have for on and go to. Now, in order to do this, I'm going to have to keep track of electric off so that when go to is called, I can associate electric off with not powered. So right now, we're keeping track of the current state in the machine, the overall states that are being added to the top level machine, but I need to keep track of somewhere temporarily which event we're talking about for on. So let's do this here. I'm going to say var current event ID, which is going to be of type states or events, is null. So we'll just keep track of this guy, and I can say for my on function, current event ID equals event. So that just kind of keeps track of it for me. And then my go to is going to take a state ID, and I want to associate that in order to have the transitions. Now what that means is my state itself is going to have to keep track of the possible transitions that he might go through. So let's go find that state class that we defined and add in val transitions, which is going to be a mutable map of equals mutable map of, and he's going to be from events to state. And so now I can come down here and in my go to, I can map that up. So the first thing I need to check is, do I have a current event? Then I need to say, do I have a state that I can put this transition in, and then set up the transition. So I'm going to say current event ID question mark dot let Well, I need a machine as well. So machine question mark dot let machine, and this one event ID, and then machine dot current state. If he exists, then inside here, I can say state.transitions sub event ID equals state ID. So a nice simple, oops, which one? So he states. Oh, I think I might have defined that wrong. Let me check here. What did I want to do? Oh, where's my transitions? Oh yeah, so he should be the state ID. So let me look at transitions. He should be states. That's what I get for choosing bad names. So this is going to keep track of when I'm in this state. If I get this event, I'm going to go to this state ID. So we're defining that inside the machine. So now this wonderful little mess that I defined here looks just fine. I mean, it actually works. Now it's not great, but it should work. So I'm going to go ahead and copy over the stuff from my little example I'm working on here, so I don't have to type it all again. I'm going to indent these. Something kind of like that. So now we're defining the transitions between these states. Now, again, this is gross. This is not going to be our final product. We do need to tell the state machine what his start state is. So in our state machine, let's see, where's the state machine again here? We've defined current state, so we need to set the current state to a given start state. So what we want to have is inside of our state machine, have a little fun. Actually, this is outside of that for now. So fun start state, val state ID, states, and whoops. And so we'll say machine question mark dot current state equals state ID. Actually, that's not what I wanted to do. Let me look at I think I messed up my definition of my state machine. Why was I wrapping those? Actually, I don't need hold on a second. Where was, so the states have that map in there. Okay, so current state is going to be machine, state ID. There we go. That's what I wanted to have it do. So this is going to put us into a given start state. And then anytime we're transitioning, we can take a look at that start state, look at his transitions, apply the event, and see where we go. So to do that in our state machine, we can have a handle method that takes an event and he's going to look up that event and change the current state based on that. So we'll do something like states sub current state, so whatever that current state ID is, and then question mark dot let. I'm defining something wrong here. So states map giving us that state object. try to specify it explicitly. States to state. There we go. So we should say current state, let. That's better. This is where it gets fun because of all these nulls and things like that. So then we have our state. We can just say current state equals state. And val cannot be reassigned. Where did I? Oh, do that. There, that should go. Okay, so this is our simple little state machine. Once we've defined him all, anytime we handle an event, we're making sure that we actually have a current state so we can do something with it. And then looking up the transition based on the event ID. Oh, I didn't do the transitions. There we go. Transitions sub event ID. And what is he not happy about here? Huh. Let me just do this for a second here just to see what that thing is. States, state ID, transitions. Oh. So let me just write this a little different. The problem here is that transitions could be null, and therefore I couldn't do the lookup on it. So let's do a couple lets here. So this is going to be state. And then I can say state with transitions, dot transitions. And what does he not like about it there? Required nullable state. Oh, I did it again. There we go. Okay, I got to work on that modeling a little bit. We'll see if we can clear that up a little bit later. So what's going on in here, if we have a current state, if we're able to, a current state ID, or current state that we're at, if we can look up the state map that we want to work with, grab his transitions, find the event, and then change my state. So it's a pretty standard lookup in a state machine situation here. Let's now see what our definition looks like. So we defined all this. Let's add in a start state, which is going to be events dot powered, or not events, state dot states dot not powered. There we go. So that should define our state machine. I should now be able to say machine question mark dot handle events dot electric on. And let's see which sequence did I want to do here. Let's go ahead and copy these guys. So we're going to do an electric on, electric off, electric on, and then a couple of claps. And let's put in a little thing in here when that transition happens. I'm just going to put a little println so we can see what's going on here. Changed to state $state ID. Let's see what happens when we run this, if this actually works somewhat. There we go. So change to not powered. That's that initial setup. So when we set the initial set there, or actually, did it start with powered? We had not powered. So start state. So he's in not powered, and he gets electric on, go to powered. Why is he changing to state not powered? Because I set my start state to not powered. And this is only printed when the state changes with a go to. Oh, I should put that in handled. That's not where I wanted to put it. Where is my handler? There he is. That's where I wanted to put it. Now it's going to work okay. Apparently it did not work okay. So we have our lights on, blah, blah, blah. So we're starting in not powered. Not powered should be in there. Let's do a little dump and see what things look like. Machine does not have any data. Let's make him a data class. Oh, actually, we'll just define a toString. Use our little generate toString. States and current state, that looks good. Okay, now let's see what we got inside there. States is empty. So that's a problem. Did I not add anything to him? So state, that's the class. So when I call state, I require not null. Oh, I'm setting the current state. No. I should have machine substates state ID equals state ID. And only safe or allowed. Oh, because again, he can be, I can do something kind of like that. So this is an alternative to doing that let that I did before. I could have said machine states let, set that be the state map, and then inside of there said that state map sub state ID equals state. Or I can omit the let and just directly go, but then in that case, I have to explicitly name the function I'm calling. So now we should be in good shape. So you have state lights on is a state there. Let's actually have our state dump his data as well. There he is. And we will do a generate toString. And let's see how that looks. It's going to be one long line. Okay, so the ID is lights on, no transitions. So the transitions aren't getting set in these guys. So let's take a look at when I need to define, when I do this state here, I need to set current state as well as what I just did. So the current state thing that was here, I still need to do. So machine current state equals state ID. Now we'll be good. Or not. So transitions. Where is the on? So we set the current event ID. We have our current state set. So we have a machine, we have a current event ID. We're getting the current state and doing the transitions. I'm going to put a breakpoint here because something is acting a little flaky. Could be my mind. Okay, so we have state ID is not powered. Let's step forward. Whoops. I'm gonna have to put, sometimes the debugging is a little interesting here because of the way that it handles the nested calls. So let's stop him and redebug him. And I'm gonna continue. So we know that we have a current state. So we're gonna take that state, transitions, event ID equals state ID. So transitions is empty there. Let's step over. And now transitions has somebody inside there. Electric off goes to not powered. Okay. So that was from state not powered. That doesn't look right. I think my data definition up top was wrong. Or down at the bottom here. So not powered, we have electric on goes to powered. So he says state is not powered. Event ID is electric off. Where is that coming from? Okay, I've got something just slightly off in this. So what we'll do is we'll take a break right now. I'm just going to get this fixed up. And once I have this fixed up, the rest of the example should go much simpler. But I got some subtle little silliness in here. I will fix that, and then we will start back up at 8:35. Okay, so there were just a couple little things I had mixed up in there. One of the things I did to make this a little more obvious was that I pulled out the current target state that we're working on building as a separate piece as opposed to reusing the piece inside. And then there were just a couple little references that I had wrong. But now everything is looking good here. So we have all our proper state machines set. The state transitions are exactly what we'd expect to have happen here. And poof, we have a little state machine. Now this definition was kind of gross. I mean, especially when you look at things like there's a lot of null checks going on in here. And we want to try to make this so that it's going to be a little simpler to define as well as making it simpler to use. So next thing I want to try to do, just to try to get a hold on all these functions that are flying around, is I want to set it up so that the functions are, we use function chaining to be able to interact with our state machine. So I'm going to take all this mess and go into here. And let me change that to 4. There we go. We're going to keep our events in our states. That should be just fine. But what I want to try to do is pull a lot of this functionality into the state machine. What I'd like to do is, instead of having this kind of a mess here, I'd like to have it be a set of chains using dots. So what I want to end up with is something that looks like, oops, this. And you'll notice that we're still having lots of fun issues with the indentation here. Oops, what is, wow, it is just giving me all sorts of grief trying to do this. Oops. And so if we take a look at this, all of these are chained functions on state machine. So what we're going to have to do is each one of these functions is going to have to return the state machine so we can keep working on it. Now, a lot of the functionality that we've got is going to stay pretty much the same. We're just moving it inside the state machine. So let's take a look at that state function that we had. This guy here, I'm going to move him inside the state machine. So there's my state machine. Let's put him in there. And so he's going to get that state ID coming in. He's going to be updating current state ID, our current target state. Let's move those variables inside there as well. So these guys, which are being used temporarily during the build, I'm going to put those into the state machine. And so our state function looks good there. And if we come down here, state machine now has to actually return a state machine. Actually, let's, instead of having him out there, let's just say return state machine. And now notice how state machine.state works just fine. Now I'm going to need to actually say val machine equals just to be able to get that guy. But he's perfectly fine with that state call. Now the state call is going to have to return the state machine so we can continue this chain. So we'll come into him and we will say state machine. And we no longer need this require not null because we're inside the state machine object. So we definitely have a state machine. So we can get rid of that. We can get rid of him because now we're inside of this. He has state, so we can get rid of that null. And now we can change this back to a nicer syntax like that. And then we just have to say return this. Now this return this is a really common pattern when you're defining any type of a builder, if you're doing this build chaining like we're defining here. So far so good. Now we need to move our on function in there as well. So let's take him and move him inside of our state machine. So he's just setting that current event, that's fine. So now we look down here, that on is perfectly fine, but we need to have him return a state machine so we can chain it. And so we'll say return this at the end. And so now that looks good. Now we have to define our goto, move him in. So we'll take that, move him into the state machine up here. And once again, we don't need this because we're inside a state machine object. We know the object exists. We have our current event ID. What is it? Not enough information to return. So current event ID is events. It's probably because of the stuff inside of this guy. So we'll get rid of the machine because we're inside this. There we go. And we're going to have our goto, again, return state machine. So we can continue the chain. And now we'll see down here, our chain is looking really good. Everything is with that state object. We can return that. Let's move our start state in. So just by enclosing this inside of an object, we've gotten rid of a lot of the null checks that we had to do. Things are a little bit simpler to deal with. So now down here, we need to deal with handling. At this point, we know we'll have a machine, so we're not going to have to have that null check anymore, but we do need to move the handle function. Oh, machine is a unit. It's state machine not return. Oh, start state didn't return. There we go. Now we should be okay down there. Okay, and what is the little error that we have up here? Oh, we need to return it. And so now if we try running this guy, he should give us the same results. But that's a little bit cleaner because we've collected all the building into this state machine. Now, typically with a builder pattern, you don't have the object itself do the building. You'll have something else prepping the data and then setting it up so you can build your final object. So we're going to want to move toward that direction a little bit more. So let me take a look here. Blah, 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 blah. So one of the problems that we have with this approach is there's nothing preventing us from doing something like this. They're all just generic functions on this state machine. So it'd be really nice if we had some way to restrict the calling order so you can only call certain objects in certain states. And what we can do to do that is define some interfaces. that represent which sets of functions we can call at any given point. And instead of returning the full state machine after each one of these functions, we restrict it to just a certain interface that says, what are the valid next functions? So let me copy this one. And we'll come into here, make that 5. And let's see, what was the next one I wanted to look at in here? So we got him. So what I'm going to do is I'm going to define some functions. I'm just going to call them A, B, C, D as separate subsets of functions that are going to be valid to call. So I'm going to come down here and let's see, I'm in the right file, right? Yeah, okay. I'm going to say interface A. And if you can come up with good names for these, that's fine. But it's kind of hard to come up with good names when you have a lot of these, because depending on how your construction goes, these may you may have a whole bunch of these. Now later on, when we get down to the proper builder patterns inside Kotlin, we're going to get rid of these. But as a temporary step, we basically want to restrict what chunks can be called at what points. So interface A is going to represent the very first thing we can call. So he's just going to be, when I call state machine, well, actually, I don't want that. Where did I use A? Oh, I'm actually creating a separate builder. Okay, so we'll keep that in there. So the very first thing I can do is call the state machine, and he's going to return something of interface B, which is going to say, once I have a state machine, what are the things I can do? And so he's going to say I can add a state, which is going to be state ID states, or I can call start state, which takes a state ID like that. Now, the start state is kind of going to be our final function that we call. So he's going to actually return the state machine itself. But if I call state, I want to go into another subset of functions that I can call. I'm going to call that interface C. So in interface C, once I've defined a state, what's the next thing I could do? Well, I could just go ahead and define another state. That would be a perfectly fine thing to do. So I'll just copy that function. I can do an on, which is going to pass an event ID. And that's going to go to interface D. Or once again, once I've defined my state, I can call start state. So I don't have to have any type of event transitions for a state. I could define a state and then immediately go to the next sub to define the start state, which ends things off. Now interface D here is going to be the what happens after an on. Well, the only possibility after an on is you have to specify a goto. So I'm going to say go to state ID states, and he is going to go back to the C interface. So at the C interface level here, I can define another state, I can do another on underneath the same state, or I can do my start state. So this limits which things you can call in which order. Now what I'm going to do is define all of this, instead of having the state machine itself do the building, I'm going to define a new class to help me do this building. So I'm going to have a state machine builder, which is going to implement A, B, C, and D. But because the functions only return one of these interfaces, it limits which functions you can call in that chain. So in my state machine builder, I'm going to move a lot of this type of functionality in. So let me get the temporary stuff here. We'll take them out and put them in the builder. Like that. I'm going to need to go back to that whole machine thing, because now somebody else is defining it. And when you initially create them, you don't have that other piece of data there. And let's move a bunch of these functions. So let's do our start state, go to, on, state, those guys. We'll move those out to the builder. And those are going to need to match the interfaces here. So we'll see this guy here, he says he hides a member of super type B, needs the override function. So we're going to add an override in him. Start state should return the state machine, so that's good there. And he is going to say machine current state equals that. And then we return machine. We should do a requires not null, require not null. There we go. Machine. And what I'm going to do here is, because I know I'm not using this in a multi-threaded situation, this is one of those few places where I'm going to put a bang bang on there. So I'm going to say I'm checking to see if it's not null. Nothing else is changing it. Now, of course, somebody on the outside could do multi-threading. I'm going to wave my hands at that for the moment. But down here, I'm going to say, hey, I know this thing is really null. Try your best not to use this. I'm just doing some hand waving at this point. Now, goTo needs an override. Put him in there. But he no longer returns a state machine. He actually returns a C. So I'm going to change that to be C. We're still returning this, which is the builder, but the builder implements C, so that should be just fine. So this is, we're going to need that machine guy in here again. I should have just left that instead of changing it in the previous example. And then I can say here machine.states, and that should be good. Let's take a look at this guy. So on, he's again going to need that override because he's in the interface. The state, instead of returning state machine, he should be returning a D. And that all looks good. What's going on? Corresponding is named event ID. Yeah, we can go ahead and make that to match. And this one is probably just state ID. Okay, so we'll rename him. And that's just done, the Kotlin compiler checks that just so it's a little bit more clear how these overrides work, if they have the same name or not. So this guy here needs an override, and he needs to change his return type. We're going to do our machine fun here. So machine question mark dot let machine blah, 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 and then move that into there, and then machine dot. And so now he should be good. And let's see, what else is missing here? Does not implement the state machine function. So we need to move the state machine function in there. Where was he defined? There he is. So he's going to be, need to do an override. He's going to be returning type B. And what do I want to do with this? Oh, yeah, machine equals that, and then return this. Okay, so far so good. And let's make these all private so nobody on the outside can mess with them. And then I think the last thing we need to do is have a function to create the state machine builder. Let's see, which should return our function of A. So we'll have fun state machine builder. It's going to return an A, and I'll just say return state machine builder. Kind of like that. So now, inside of our main function up here, we're going to say start with a state machine builder, and then we're going to call state machine on him. And now notice all the little return types listed here. It's actually kind of helping you see what actually is getting called. Oops, he should go there. And let's take a look at what happens if I try to swap the order of these things. So if I take this goTo and I move him down a line, Notice how now that on is no longer valid because I would have had to specify that goto based on that little C interface, I think it was, or no, the D interface has to have a goto. So without having that goto, I can't call that on. So this has now helped me a lot. I can't call things in the wrong order. It's getting a little bit better. We can do better than this though. Okay, any questions so far? Okay, let's see what our next thing is going to be here. Let's, while we're at it, add in an action that can be performed when we're transitioning states. So we'll take all this stuff, go to our next file, change his name, and pardon me. So let's see. So what I'm going to do in my builder, I'm going to add an action function. So where's my state machine builder? Here he is. So I'm going to add in an action function here. And I'm going to change my interfaces just a little bit here. So let me just double check what I've got. Where's my interfaces? So A, state machine B, state C, start state, state machine, good. C, state on start state, CD, state machine, looks good. So what I'm going to do is in step D here, I'm going to add in an option that instead of just calling goto, we can say perform an action before a goto. So I'm going to say fun action is going to be just a little lambda that you can run there. And he is going to go to E. And then interface E is only going to allow that goto. So basically what this lets me do is it lets me have this optional action before a goto. I can either call goto directly or say action something and then goto. So we just added that piece in, which is kind of nice. And let's see here. So in this guy, current state actions, blah, 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 actions. So let's look up the machine (let machine). I'm trying to avoid these bang bangs that I have here. These are assuming that everything was done right. I want to use these lets to make sure that things actually exist as opposed to getting a runtime error on this. Now with the lets, I probably should have a question mark colon with a run and then report error. So we can do some nice error reporting. But again, that's going to happen at runtime. So it's something that's probably not ideal. I'm just going to leave it for now. And then we'll say machine dot states sub current target state. There he is. And if we have him, then we can say state dot actions, which we'll define in a second here, sub what I call current event ID equals action. And I should actually do again with the current event ID like that, and then something like that with event, and then we'll just keep track of an action. This only allows for a single action inside a lambda to be performed, but that should be pretty good. So I need to add E as a possible interface so that the return this works, and then inside state we need to define the actions. So let's do where's state here? I call this state with transitions. I changed the name just to have a little less confusion between states and state. So let's add in here a val actions equals mutable map of events, comma, some lambda that we're going to run. There we go, and that all looks pretty good. So now we should be able to add in a let's see, an action. Am I looking at the right one? I don't think I'm looking at the right one here. There we go. So let's do it on when state is powered and we have a clap. So let me fix these up again here. So when we have a powered and we get a clap, let's add in an action there. Something kind of like that. So now we'll see that D allows us to do this action, which goes to E, which forces the goto. But D also allows us just to do goto. So now, once again, we're forcing the possible call chain here. And let's actually implement that action so it actually does something. So in my handle, oh, my state machine's up a little farther. So in my handle function here, before I actually do the transition, I'm going to do an action if it actually exists. So I'm going to say, let's see, so state with transitions. He's going to have that information. Dot actions. If we have an action for this event ID, then we'll invoke it. Now, this question mark dot invoke, keep in mind that running a Lambda, if it's nullable, you can't just put paren there. So we'll see in this case, it's going to say, hey, it has a nullable type, blah, blah, blah. So I have a choice here. I can either do like a let and say action, and then just call action, paren. That'll work. Or alternatively, I can call invoke, which will call that Lambda as with a name to it. Unfortunately, you can't just say question mark dot paren. It just won't work syntactically. So these are your choices. You can either write it like that or write it like this. So I'm going to comment him out. Basically equivalent to something like that. Okay, so let's see if this will actually print out clap when we do that transition. So I'm going to run him. And something is not right again. Wonderful. Well, I'm going to make a note here to fix this because I don't want to spend any more time trying to debug this. There's some little subtle thing. And let me just make a little post-it here so I remember after class. This is in week 1006. And then we will get him fixed and see that actually run. So the next step that I want to do here is just show a slightly different approach to do some of this. So instead of using this chaining like we've done, which as we can see with when we format it, it gets all messy, and this is kind of awkward the way it is. I would like to set it up so that we can use apply to scope things nicely. So what that apply would end up doing is taking a state and doing something interesting with it. Taking the state machine and doing something interesting with it. So this one, I think what I'm going to do is I'm just going to copy this code that I already have over. Let me just take a look and see how different this one is. Oh, it's actually pretty similar. I'm actually not using the builder, am I? Okay, let me actually copy over parts of this and then I'll gut it. So we'll go to 7. And this is just a little alternative that kind of gives you a little idea. Whoops. Week 1007. That's better. So this is just a slight alternative just to kind of show you how we might be able to scope this as a movement toward where we want to get to. So I don't think this one's using the state machine builder. Yeah, it's not. So I'm going to get rid of him. And let's just see that everything works. Oh, it looks like the code is, well, can I use the existing state machine? Let me see if I can copy my existing state machine over and make some tweaks, because it'd be nice to have the consistency. So we'll take our state with transitions, take our state machine, come over to him. And I'm going to call it state machine X just to get him out of the way. And I'm going to have a whole bunch of issues here. So what I'm trying to do with this is I'm going to use the apply function to do some initialization. And we'll see how this is starting to look a little bit more like a little language for us. So if we take a look in here, I'm creating a state machine instance, and I'm explicitly setting the current state to some state here. And I think it did some imports. Let's get those out of there. Oh, this is doing these things a little differently. Let me copy back over from the previous one a couple things. We'll just take those and define them outside of here. I'm not using those. Going to get rid of him and do that. That's a little cleaner. Okay, so what we're doing is we're going to create that instance, set the state. We're going to call some explicit add functions now to add these states. And notice how I'm using a constructor here to create that state object and then tweaking his definitions. We're going to talk about this goes to in just a second here. But let's first of all take a look at that add function. Where's that goes to defined? That's in state. We don't want that anymore. Well, we'll fix him up in a minute. Okay, so let's define our add function to allow us to add in a state with transitions. To our state machine. So that's going to be an add function inside state machine. And we're going to take a state with transitions. And he's going to take the state with transitions that we initialize using an apply. So he doesn't return anything. So let's see. So add, he's going to say states sub state with transition dot state ID equals state with transitions. Boom, just like that. That should be all we need for him. And now this apply is going to call functions defined inside state with transitions. So this guy here, goes to, is a function that we're going to be defining, taking an event as a receiver and a state as an argument. And we define it as an infix function, so we don't need the dot syntax or parentheses. This works for anything that has a receiver and a single argument. You can define that. So let's define goes to. Let's see where it was in here. This is the one. I've changed a little bit about how I want to do this example, so there's a little bit different syntax. But this is going to be defined in state with transitions, which is in here. And I'm going to make it be events goes to states. And so this function, by putting infix, allows us to have the receiver on the left-hand side, and then a space, and then goes to, and then the state ID on the right-hand side. Now what we're going to do, though, is because in some cases we want to add in another function to perform, like this and does, what we need to do is have this function call return some kind of an object that defines that and does. So what I'm going to do with this is in our goes to, we're we're going to return a little object we're going to call transition thing. This is just a little temporary guy. And all he has in him is a, all he does is keep track of a state and an event ID so that we can call a later function on it, and does. And I'm going to actually lump these together. So let's say class transition thing. He takes a states object, and he's going to have the event ID, which is an events object. And inside of him, what I had done in this previous example here is I used a extension function. I could actually define it inside. That way nobody else can call it. And I'll just say infixFun and does. And so actually this should be a state with transitions. There we go. So this is going to allow us to add that action if we call and does. So this transition thing, he's returned from this guy. We're creating him, saying we're going to pass this at state with transitions. Notice inside this function here we're defining, this is an extension function on events. So this is defined as an events object. But I really want to return the this that's the surrounding class. So in order to do that, I need to explicitly qualify this with at state with transition. So I'm basically saying which this I care about. If I just said this, it's going to take the closest this, which is the receiver for goes to. I need to just push it out to say the class instance that contains the go to. And that'll do that. So that should define my goes to. Let's see what we got up here now. So this is all looking pretty good. So we're defining the state with transitions. We use apply to let this goes to function be visible and actually hook up electric on and powered. And then this one here, we're doing that same kind of thing, but the goes to is returning a temporary object, which gets ignored here, by the way. And that temporary object allows us to add in that action for us. So let's see if I can get rid of some of this other garbage. And I don't need that. I no longer need all my ABCDEs and all that fun stuff. And so this approach here, kind of different from what we did before, but it leads toward where we want to try to go. Notice how these applies are making these things look scoped and actually forcing the scopeness. And if I formatted this code, it's all going to be perfectly well formatted. So let's see what happens when we run this guy. See if it actually runs. There we go. Notice that my clap got called, which is what I wanted to have happen. So I must have had something right in this example versus the previous example. Some little silly thing in that previous example. But this is starting to look a little bit more like the language we want to define. Okay, any questions so far? Nope, just syntactic sugar. So this call to goes to is exactly the same as if I had typed this. And you can use both syntaxes. But you'll notice the difference in the way the syntax looks. With using that infix, it's much more readable. It looks like you're speaking more kind of like English than actually having a function call. But both of these calls are exactly the same. Actually, let me put that up here. Yeah, I should have said that earlier. Let me put this up here. There we go. So it's just a nice little syntactic sugar thing that allows you to write the function without the dot and the parens. Okay, let me just make sure I didn't break anything there. Okay, that looks pretty good. So far, so good. So now let's start moving this more toward something a little bit more readable. And let's see what we're going to do here. I'm just taking a look at my notes. So we'll start with this code. And come up here and change that to 8. So let's see. So between 2.7 and 2.8, let me look at the diff and see what's going on with this guy. Okay, so let's take a look at what I'd like this to look like. So this is what I'm going to be shooting for in this step. Is code that looks like this: machine is state machine, start state, states powered create, blah, 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 blah. So a few different looks from this. Note that I'm not using the applies anymore, but the structure is the same. I mean, it really has the same type of feel, but it's a little bit more readable because we don't have all this extra syntax to do the add and the applies. We just have stuff that actually happens in there. So that's where our goal is going to be. Let's see what we can do about this. So we're going to need a top-level function for state machine. And what I want to do is have that create the state builder for us, do the initialization, and then return it. So if we take a look at this, state machine is going to be a function that takes a lambda. That lambda is going to do all of our initialization of the builder and then build it. So the builder is going to have a start state inside of it. He's going to have a create function. Whatever this returns is going to have the go to. So it's going to have that that transition thing is going to have that goes to. And we should be in pretty good shape. So let's define, first of all, this state machine builder. And this is going to be the first time you're going to see what a real builder in Kotlin is supposed to look like. And the basic structure of a builder function is that you're going to take a lambda that we're going to call a init. And that lambda is going to have a receiver of the builder itself. And the lambda is going to be a function that runs using that as a this. So we're going to create that state machine builder. We're going to initialize it, and then we're going to return the value. So the state machine builder is going to keep all the stuff he needs internally, and then he's going to actually do his build and run. So my state machine builder is going to look like this. Let me fix these guys up here. And whoops, I called that was the state builder. I want my state machine builder. Let me grab him. There he is. And what you tend to have with this is you have several builder classes, one for each type of object that you're constructing. And each of them will have a build function to say what their output is. So the builder is going to do some internal things when you're inside that initialization lambda. And then once we call build, it's going to return the finished object that's being created. So let's start with our state machine builder here. We're going to actually create a machine. So now we're no longer going to have that, nullable in there. Let me make this private and make this private. So we're just going to be filling in some data. Oh, we want that actually to be visible so we can set it. And then we have this create method to create a new state. So we're going to pass in the state name. We're going to create a new state. And notice this looks very similar to that other function I was talking about. We take an initializer that has a receiver of the builder, and then it's used to initialize it. So we create the builder, call init, call build to get the result, and then we're going to return that result or do something with that result. So in this case, once we've built it, we have our state, we're going to add it to our machine. So it kind of builds this thing up recursively. Our build itself just says, I'm going to take my machine, set the current state value, and then return it. So that's my state machine builder. When you call create, he creates a state builder. Let's look at him. So the state builder has a state ID that we pass in. We're going to create the actual state object that we want to return. Goes to is going to fill in the transition information and return that little helper class, the transition thing, so that we can do a goes to if we want to, or we can go do the action if we want to. And then build just returns that state object. So notice how these two functions really have kind of a very similar structure to them. We create the thing we want to return. And again, let me make this private because I don't want to expose that. We have functions to do initialization, and then we have a build function that just returns it. So this now allows me to have this structure up here. And it looks really nice now. So our state machine, we define state, start state, and you can have properties you set like that. And then we're calling create, calling goes to, calling and does. Now notice and does doesn't get the same syntax highlighting. That's because he's not defined as a extension function. The other ones here, this, what was that function? The goes to, he's defined as an extension function, and that's just the way that the highlighting works inside Android Studio for when it's highlighting Kotlin. It highlights the extension functions but doesn't highlight the normal functions. Okay, so now we have something that's actually looking much, much nicer. Let's go ahead and run this just to make sure it works. There we go. We're getting all the same functionality. And I'm liking this much, much more now. Okay, but it's still a little bit verbose. We have this events.electricOn. We have states.lightsOn. It'd be really nice if we could define these using something like a sealed class or a sealed interface so we don't have those qualifiers that we need to deal with. So let's take a look at what this might look like. I'm going to go ahead and copy what I have. Change that to a 9. And here's what I'm going to change. That's going to be the biggest change there. So what I'm going to do, I'm just going to copy this stuff from up here, paste it, and what did I want to define that as? So event, where was event defined? Oh, actually I don't. So let's say sealed class events. I'll just keep it events like it was. And that'll be events. Events. Actually, I'm going to make that, make these data objects. So we get a nice toString in there. And because we don't have any data that we're storing inside here, I'm going to change this to a sealed interface. And then I can just get rid of these parens. Kind of like that. We'll do the same thing here. We'll make him a sealed interface. And he's just going to be states. Make these all data objects so we get our nice toString. There we go. So there's our nice data definitions now. And let's take a look at what we've broken all over the place. Looks like it's mainly going to be this stuff. So I should be able to just say not powered. ElectricOn goes to powered. Get rid of him. And then get rid of him. And that's not much nicer. So now we've reduced our verbosity in this by quite a bit. Let's just make sure that this still works. There we go. That's coming out just nice. So this is one of the places where I think that sealed interfaces and sealed classes really shine. You can have these values that kind of feel like enumeration values, but you don't have to qualify them for one thing. And you could actually define them across multiple files if you need to. So this is a really nice state to be at with this. And we've seen how state machine creates that builder, creates the state builder. And then we use this normal builder pattern in Kotlin by having the function take in that lambda that works on the builder that we're creating, calls a init on that builder, and then calls build on the builder to actually finish up creating whatever objects we need, and then we return it. So this is what we call a type-safe builder inside Kotlin. Now there's a couple little wrinkles in this. Let's see if I can actually get this to work. So we'll come into this. One of the things that happens is when you're in the scope of a state machine here, you can call state machine objects or state machine instances inside here. So I could say something like notpowered.create, like that. And that's not ideal. You really don't want to see something like that because now we're nesting creates, and that doesn't really make sense. So what we can do to get around that is mark the builder objects that we're creating as DSL participants, as builders themselves. So to do that, let's see if I can remember how to do this. I haven't done this one in a while. We can define a new annotation class that, let me just call it builder, and mark that as a DSL marker. Now this allows me to annotate classes, and DSL marker is a special annotation in Kotlin that the compiler does a little extra work to restrict where you can make calls. So what I'm going to do is I'm going to put this builder annotation that I've just defined on my state machine builder and my state builder. So on my state machine builder, or this is my state builder here, I'll just say at builder, and then on my state machine builder, the same kind of thing. And what this will do is this should restrict it so that these functions are only allowed directly in the scope of the state builder. And let's see if now I can do that create thing that I was just doing. There we go. So now we'll notice that I can't nest these create calls anymore. So up here at the top, once I'm inside the create, I'm now in a state builder. I'm not in a state machine builder. And the Kotlin compiler will now say, hey, you can't call it in this context. If you want to escape out, you could explicitly call out, but that's a little tricky with this because we already got a receiver, and you'd need to have a, what do they call it? A context receiver, which is something they're working on in Kotlin. There's a couple little changes coming. I don't want to go down that path, but you could escape out of this. Normally, you don't want to. So this is helping prevent calling inside this context functions that are defined outside here. And that's really super useful. Did that make some sense? It's the create function itself. So because the create function is defined inside state machine builder, and state machine builder is annotated as a DSL marker builder, we can't call his functions inside another builder that has that same annotation. So cannot call functions defined in the parent, let's say the containing builder. Without the DSL marker annotation. Oh, come on. We could call any function in scope. There we go. So that's a really nice little thing you can do, and you generally want to do on your builders. You can define different DSL marker builders to have different groups of contexts that should be mutually exclusive. Most of the time when you're defining this, you can just define one and then just annotate all of your builder objects with that. And then that'll restrict the functions defined in that builder object from being called within a nested builder object. Okay, any questions on that? And so now we've gotten down to something that I think looks really, really nice here, and it's pretty lightweight. Oh, what am I? Can I? No. I'm wondering, can I say infix here? I don't think I can with a. Oh, maybe that would be nice. Let's see. Oh, that used to not work. Ooh, nice. I like that even better. So now it's like we don't have the dot syntax there anyway. Yeah, it used to not allow that to define an infix when you had a receiver. So they must have fixed that up pretty recently. That's actually really nice. And let me actually change the handle while I'm in here. We'll do an infix on him as well. And then we can change those. To do something kind of like this. There we go. And so this really gives you a nice, concise way to specify things. There's some control in the scoping. There's some flexibility on how you're setting these builders up. Just keep in mind, you're not directly defining the objects when you use this DSL. You're defining a builder that will create those objects for you. And then once it's done running its initializer, it returns that. So it's kind of a two-step process. When I showed you the earlier one, when we had all those applies, we were actually creating the objects ourselves and then calling the functions directly to just fill in those objects. The big difference you get out of that is when you use a builder like this, the object can have the object itself can have everything set up as a val. So start state, for example, if we had the start state listed inside the state machine itself, the start state could be a val, and you don't have to do it. Notice here how val, whoops, that I don't think that needs to be a mutable map. Let me see, where's the state machine created? So we create the instance of it and then we're filling it in. So what we could do is a slightly different approach on this if we wanted to. Let me actually make a new folder, a new package. So week 10, 11. And then let's copy that main into there. And let's say that one thing that you can do with this is you don't have to make things as mutable as they used to be. So in the state machine here, instead of having this be a mutable map, what I could do is pass that in as a val states map states state with transitions, and then get rid of it there. Oh, that add function wasn't being used anyway. And then instead of creating the state machine and then set, what we can do is keep track of in the builder. Let's do a private val states equals mutable map of states, oops, and state with transitions, something kind of like that. There we go. And then what we'll do is instead of creating this machine and filling in the details, we'll create the machine in the build so that we can pass in a non-mutable form of this. So down here, this would become state machine passing in states to map. So we're actually creating a new copy of it and then filling in the start state. Now we could also pass in the start state. So we come down here and say start state states, whoops, and then just change this to say start state, and look at what this lets us do. Now inside of here we don't have to have the current state. be nullable because we're not actually setting it. Now we're actually passing it in, and when we get it passed in, we know it's not null. And so we can do stuff like this. And this is one of the advantages of when you start using objects that are more and more immutable. So let's fix this guy up. So we have him, we have start state, we can get rid of the apply now. Start state is being set as a nullable here. So what we might want to do is have this guy say start state let can pass that in as an it. Otherwise, throw, let's see, a legal state exception might work there. No start state defined, you're evil. Something kind of like that. So now this build is actually validating. By the time it gets to the build, if you hadn't specified that start state, boom, we get a little message on it. And then this would be just states instead of machine.states. And I think that's it. So this is another slightly different approach you might use on a builder. Change to allow state machine to have immutable states and non-null current state. So this is another thing you can have your builder do, and another advantage to a builder pattern here is he's collecting the data in order to create the object that we're returning. And so we have a bunch of little temporaries inside of here that we use to collect the data during that initializer. These functions help set them up. But then when the build is actually called at the end, boom, we just go ahead and return that, and then life's peachy. Okay, any questions on that? Let me just run that just to make sure I got that one right. And I'm going to get rid of, let's see, that I had that comment in the previous one, right? Yeah, let me get that comment out of there so it's not clouding things. Okay, what is going on with these guys? Why is he highlighted? Oh, just because I was clicking on it, that's why. Okay, and we'll run this just to make sure he works. Boom, working nicely. Okay, any questions on what we've covered today? I've got a little bit more time. Do I want to hit anything else or not? Yeah, let's briefly talk about value classes. New package week 10, 12. And we'll create a brand new main inside of him. So whenever we're defining objects that contain just really simple values, like let's say we do a main here, and I'm going to define a class, oh, I don't know, int carrier. This is a good one to define. I'll just do it like this. So let's say that he has inside of him a val number int. So we might define a simple class like this. This is kind of expensive. And what ends up happening when you put ints in a list is it basically does something like this. So that if you have a simple class like this that you want to pass an object around, this takes up a whole other object just to wrap that int. If we want to be able to use that int directly and more efficiently, we can define something called a value class. Int carrier 2. And put that in there. And what is he not happy about? Without, oh, JVM inline. We have to define this so that Java can actually use it as well. But the difference here, this is a wrapper object that contains an int. Extra memory required. This one is compiled to just use the int directly. And the big advantage to something like this, let's actually, I'm just trying to think of a simple example I want to show you here. Let's say actually, let's call this a clock. And so it contains a long. So we'll make this a long, which is going to be like the number of milliseconds type thing. And then this one, we'll do the same kind of thing. And the big difference between these two is this first clock has another whole object wrapping around that long. And if you're converting back and forth between that number and a clock, it has to keep creating and getting rid of that object. This one compiled to use just the long directly. And the advantage you get here is that this is an object that can have functions inside of it. Print time. Let's say actually this is, let's just use an int and make it minutes. And so we'll do this, we'll say minutes, int. And let's say that we have a print time function, which is going to break that down. And what he'll end up doing is saying val hours equals minutes divided by 60 using integer division, and mins equals minutes mod 60, something kind of like that. And then we can just print out hours, whoops, colon minutes. And we can do the same kind of thing down here. And now we have something that we can treat like a, make it private. We can treat him like an object. Oh, private. There we go. We can treat him like an object, even though all it's doing because of the value class is behind the scenes directly using this minutes. So now if I try to do something inside here, let's say we have val clock1 equals clock1. Let's say we have 1,000 minutes. We'll make clock2 have 1,000 minutes. We can then say clock1 and clock2 print time. So now if I run this, I should get the same answers, but the second one's going to be much more efficient. So we're saying 16 hours and 40 minutes. This guy here, if you're going to be using some really simple values and it's just a single parameter coming in, it's just a single property you're keeping track of, you can do this. And it can be much, much more efficient if you end up translating back and forth. I mean, if you're only ever creating it once and then reusing it, probably not as big a deal. The place where this really shines is if you're going to be taking whatever this value is from somewhere else, converting it to a clock to use it, then doing that multiple times. This can be much, much more efficient. Or if you have a whole bunch of these, you want to do a lot of things with the wrapping of the int, this can be much more efficient. Okay, make sense? Any questions on that? Just a nice little optimization. If you find that there's you're wrapping single items a lot, this can actually save you quite a bit on the garbage collection front, and it can also help memory usage. Okay, any other quick little things that I want to try to cover before we call it a day? No, I think that about sets it up. Any questions on anything before we quit for the day? Cool. The assignment, I'm going to write up a new assignment because I don't have an assignment that matches the builders, and I want you to try that out. So I'm going to write up a new assignment that should be available either late tonight or sometime tomorrow morning. Have yourselves a great day.